right, so lesson 37 is on what we call fundamental identities. So identities is going to be what this whole little mini chapter is about. So identities are little miniature proofs. So you're proving that one thing is equivalent to another thing. So some of these you know. Like you know that secant is 1 over cosine, right? This makes sense. Cosecant is 1 over sine, right? So these are called the reciprocal identities. So sine is the reciprocal of cosecant, and cosecant is the reciprocal of sine. You're very good at those. We've been doing those for a long time. Cosine is the reciprocal of secant, and secant is the reciprocal of cosine. So I always say the C's and S's go together, but it's not the obvious ones, right? It's not sine and cosine, secant and cosecant. We're going to talk about what a cofunction is in just a little bit. And then tangent and cotangent are reciprocals. So 1 over cotangent and 1 over tangent. So those are the only cos that are reciprocals of each other. So the quotient identities are just, you know, when you write out tangent, what is that? That's the y value over the x value, right? So it's the sine over the cosine. And because cotangent is its reciprocal, we write it as cosine over sine. Okay, and then we have things called the Pythagorean identities. Okay, I think some of you guys are smart enough to figure this out. So I'm going to draw the little unit circle. You guys are bright. You got this. And on our unit circle, let's say we have a hypotenuse of 1, which makes sense. It's 1 unit, right, called the unit circle. And this point here is always the x value and then the y value. So what was the x value? It was what with theta? Sine, cosine, tangent, secant, cosecant. The x value is cosine. So we have cosine of theta, comma, sine of theta, right? That's the point. So what that means is this distance right here that I'm marking in red is cosine of theta, right? It's how much I'm moving over along the x-axis. And the part that I'm marking in blue is our sine of theta. Okay, if you were using the Pythagorean Theorem, how would you relate cosine, sine, and 1? Hallie, what do you think? You square what? Like, so you do cosine squared plus squared equals 1, right? Because 1 squared is 1, right? That's the first one. So I'm going to write it as sine first, though. So sine squared plus cosine squared. Okay, you will see this all the time. So if you see sine squared of 54 plus cosine squared of 54, it's always equal to 1. Okay, they have to be the same angles. All right, so there's 2 more versions of this, though. This is the main version, and I, as a math teacher, only have this one memorized. Okay, the other 2 we just get from this one. Okay, so what if I decided that I wanted to balance the equation? I wanted to divide everything through by cosine squared. So don't write this little line here, but let's say I divided everything through by cosine squared. Well, what would happen? What's the sine squared over cosine squared? What does that become? It becomes tangent squared, right? What about cosine squared over cosine squared? It cancels and becomes what? It doesn't just go away from completely 1, right? 1 over cosine squared? Secant squared. So write the second version of that. So divide everything through by cosine squared. And you get tangent squared plus 1 equals secant squared. Okay, there's a third version. So the third version is dividing all of the sines and like the sine squared, cosine squared, and all that by sine squared. So if I divide each thing by sine squared, again, think what you have. So what's sine squared divided by sine squared? 1, right? What's cosine squared divided by sine squared? Yep. What about the last one? Cosecant. So the reason I don't have these memorized is because I always get them mixed up their order that they go in. Okay, so like I'm always like, ooh, wait, is it 1 plus cosecant squared or 1 plus cotangent squared? And so I just really quickly write out sine squared plus cosine squared equals 1, and I just divide them out in my head. Okay, you can always do that. So don't try to memorize every single one. But when you see things that involve 1s and something squared, it's probably one of these Pythagorean identities. So when we get to these steps where we're trying to do these little mini proofs that I was talking about, we're going to look for those things. All right, so cofunctions. So this is the next one. So cofunctions are functions that have similar shapes, but they involve some kind of like shifting. So if you think about sine and cosine, right? Do you guys remember how sine looked like this? Oops, down further. and cosine looked like exactly the same thing, only shifted to the left a little bit. It looked like that. Does that make sense? They're the same curve. They're just shifted. Okay, think about cosecant and secant. What do those look like? The little u things, right? And those would be the same if we just shifted them over. Okay? Tangent and cotangent, almost the same, but what's different about them? That's a shift and a reflection. Okay, so cofunctions have similar shapes. Okay, not only do they have similar shapes, but there's a reason we call them cofunctions, because they're complementary, right? Do you guys remember the word complementary? So if you have, like I wrote here, sine of 47, that's actually the same as cosine of 43. 47 and 43 add up to be 90. So if I did something like sine of 65, right, what's it going to be the same as? Cosine of 15, right? You lied, it's 25. I was going for it. I was like, okay, I don't have to do any mental math today. I'll let you guys do it. Yeah, it's 25, right? 90 degrees. We're thinking 180. All right, so what about tangent of 28? It's going to be the same as cotangent of 62. Exactly. Cosecant of 89. Secant of 1 degree. That's right. And then we get to the cosine of pi over 6. And that starts to make you a little uncomfortable because you're like, wait, what? Pi over 6? Okay, that's not 90 degrees. But what's 90 degrees on our unit circle? Pi over 2, right? So if I want to take my pi over 6 and add it with something to be pi over 2, you could do pi over 2 minus pi over 6. Or you can also think about the degrees. What's pi over 6? It's 30 degrees. How much more do I need to get to? 90 degrees, I get 60, so it would be pi over 3, right? Does that make sense? But if you get common denominators, you get 3 pi over 6 minus pi over 6, which is 2 pi over 6, in other words, pi over 3. So this ends up equaling sine of pi over 3. Do you see how that works? So in textbooks, you'll see this little table, and it will look like this. So it says sine of pi over 2 minus theta. Well, this is just 90 degrees, right? Okay, if you have 90 degrees minus an angle, it's the same as the cosine of its complementary angle. Okay, tricky. What's the complementary angle of 90 minus theta? What do you add to it to get 90? You add theta, right? Does it make sense? 90 minus theta plus theta makes 90. So cosine of pi over 2 minus theta is going to be sine of theta. Tangent is going to be cotangent of theta. And so we're just getting all of the cofunctions with just theta. And it goes in both directions. So if you have cosecant theta, you could replace it with secant of pi over 2 minus theta. So we'll say also works for 90 degrees as well. Right? I just wrote the ones with just pi over 2. All right, making sense so far? Okay, so the next thing we have are even and odd identities. Okay, again, if you think back to things you know, this will be really simple. You guys are all pros of the unit circle, although some of your sketches of the unit circle on your test, I meant to give you a blank one. I forgot to print it, because some of you guys asked me for a blank one for your test, and I forgot to print it. So some of you guys sketched it in like the corner, and it was kind of funny seeing all your little sketches. You should be getting to the point where you don't need to sketch it out, though, right? So if you think about where sine of 30 degrees is, you should be thinking, okay, sine of 30 degrees, that's the one where it's just up just a little tiny bit, right? What would sine of 30 degrees be? 1/2, right? What about sine of negative 30 degrees? It's negative 1/2, right? Does that make sense? So if I have sine of negative theta, is that the same as sine of theta or no? Sine of negative 30, was that exactly the same as positive 30, like sine of positive 30? No. What was different? They were opposite each other. It became negative, right? But let's think about cosine. Cosine of 30. What is cosine of 30? It's root 3 over 2. Is that the same as cosine of negative 30? Does it go out the same amount? Yeah, it does. Those are the same. So if I see cosine of negative theta, well, I can just replace that. I can say, well, that's the same as cosine of theta. Okay, but if I had sine of negative theta, it's not the same. They're opposite. Okay, some teachers will say things like, you can pull out the negative. That's illegal. Like, can't just pull things out. But I see what you're saying. Like, I see, like, for sine, it's kind of like the negative goes to the outside. All right, so what do we think for tangent? I don't know. Is it the same or is it opposite? Ben, you know this. I know you do. Think about 30 and negative 30. Is tangent of 30 the same as tangent of negative 30? No, they're opposite, so it's negative tangent of theta. Okay, so let's go a step further and talk about, so do you see at the top it says, remember, even functions like y equals x squared are symmetric across the y-axis, and odd functions like y equals x cubed are symmetric across the origin. So let's think about that. Y equals x squared, we called it even, because if I plugged in any number like 2, see how I got 2, 4? What if I plug in its negative version? Do I get the same thing or do I get opposite? I get the same thing, right? That's what we call an even function when you get the same thing out, just like y equals x squared. Okay, of sine and cosine, ooh, that got a little crazy. If I plug in 30 degrees, do I get the same thing out over here? No, this is odd. I get the opposite thing out. So if I was at a height of 1/2, I'm going to be at a height of negative 1/2. But for cosine, if I plug in 30 degrees, do you see how we get the same thing out? It's symmetric across the y-axis. I could fold this over, and it would be exactly the same thing. But for sine, I can't fold it over. Do you guys remember what odd functions do? So that's an odd function. If I plug in 2 into x cubed, I get 8. If I plug in negative 2, I get negative 8. What happens with odd functions? Do you guys remember? I've done it on my fancy machine, and you guys were all like, ooh. Yeah, you can turn it around, and it becomes exactly the same thing, right? That's what an odd function does. So if I take the, I don't know if this will turn it around or not. Oh, I was missing that other part. So sad. But if you turn it around, it becomes exactly the same shape. It's sine of theta. You guys see what I'm saying? Okay. So cosecant. I don't know. You can go out and you can draw cosecant. Cosecant is the reciprocal of sine. Do we think it's odd or even? It's odd, right? It's not one where I can fold it over like this. Okay, think about why that's true. If I had cosecant of 30 degrees and cosecant of negative 30 degrees, that's the same as like sine, right? They're going to be opposite each other. So this is a negative cosecant of theta. And secant is going to be the same as cosine, so it will be secant of positive theta. And cotangent is the same as tangent. It's also odd, so it's negative cotangent of theta. Okay, are we understanding this? Do you guys see how everything's interconnected? I feel like you can't truly teach math classes unless you really, you teach all of them. If you teach Algebra 1, Geometry, Algebra 2, and you know how connected they are, right? So do you see the connections between things you've learned before, even and odd? All right. So it says the 3 boxes that we've had. So we had the quotient identities. I think I combined it into one box back here. Oh, no, cofunction, and then reciprocal quotient, Pythagorean. All 3 of these boxes represent what we call the fundamental identities. These are fundamental to knowing pre-calc. Did you know most of those already? Yeah, you knew a lot of them already. All right, so we're going to try to factor expressions, and we're going to simplify until we get something that's really compact, something really simple. Okay, so if I have tangent squared minus tangent squared times sine squared x. Any ideas? What do you guys look at it and you're like, ooh, what do I want to do? Yeah, factor, pull out that GCF, right? So I'm going to pull out the GCF of tangent squared x. By the way, I'm really bad. Like when I say tangent squared, I assume that there's an x there, right? It's always sine of x, cosine of x. There's always something. It's like logarithms. Like we were never like log plus 3 equals 5. It was always log of something, right? That's called the argument. There's always an argument there. So teacher pet peeve when you don't write your x's in. You cannot say those if you want to just not say them, but write them. All right, so what do we get inside parentheses when we pull out tangent squared? Yeah, we get 1 minus sine squared. Okay, I told you to look for things that involve 1s and something squared. What do you guys think? 1s and something squared. So we're going to go back here. Could I rewrite that in another form? Sine squared plus cosine squared equals 1. Can it be 1 minus sine squared equals something? What do I get when I do 1 minus sine squared of theta? What's it equal to? Nope, pull this one over here. It's just cosine, right? So that's going to be replaced with cosine squared. So let's go back here. And we're like, oh, this is the Pythagorean identity. So I can replace it with cosine squared. Okay, that's pretty simplified. Can it go any further? How could we rewrite tangent? Yeah? Close. So she said cosine over sine, sine over cosine, y divided by x, right? So if I rewrite it, sine squared over cosine squared, and I'm multiplying by a cosine squared, what happens? Yep, it cancels. Julian said, cross them out. So we get sine squared. I think that's probably as compact as we can get it, right? As simplified as possible. So we're going to leave it like that. Okay, is it equal to other things? Yeah, it's equal to 1 minus cosine squared. It's equal to, I mean, you could call it other things. But I try to get to the most simplified answer as possible. Okay, sometimes that's very, sometimes your answer might look simplified and your friend's answer might be simplified and they're actually equivalent. And you're like, I don't know which one to write. It's fine. Like these ones, I never really put questions like this on the test because it's very vague, like how far is simplified, right? So tangent to the fourth x plus 2 tangent squared x plus 1. Any ideas on what to do here? Well, there's a GCF for these two, but not for the whole thing. Yeah, what do you mean by factor? So like 2 sets of parentheses? Yeah. What's in the first one? Putting you on the spot, huh? Tangent squared plus 1. Do you guys see how we would need a tangent squared multiplied by a tangent squared in order to get this tangent to the fourth? All right, so we have tangent squared plus 1 times tangent squared plus 1, right? Do you see how the outer and inner combine to be that 2 tangent squared? So I think we're good. All right, so let's go. We have ones and tangents. Let's go back to our little chart. Tangent squared plus 1, what's it equal to? Secant squared. So we have secant squared x times secant squared x. What do you think we have? Secant to the fourth x, yep. You can leave it like that, or like I was saying, maybe your friends are like, ooh, I don't like secants, I like cosine. So some of you guys might write it like 1 over cosine to the fourth x. Okay, it doesn't matter. That's why I'm saying it's kind of like, what's simplified? All right, so how about this next one? So we have 54 and we have 36. These are not the same angles. So if they're not the same angles, we want to get them to be the same angles. All right, so how are 54 and 36 related? Yeah, they're complementary. Now I'm like, I'm going to write comp because I just spaced on how to spell complementary. I think it's L-E. Complementary. All right, you know what I'm saying. I should know that. All right, so they add to be 90. So let's change one of them. It doesn't matter which one. All right, so let's change this into sine squared. It would be sine squared of what angle? 36, how convenient. So now that we have sine squared of the same angle plus cosine squared of the same angle, right? What can we say? It equals 1, exactly. Because of that Pythagorean identity, if we were at 36 degrees, right, this would be cosine plus sine, right? Or cosine squared plus sine squared equals 1. Do you guys see what I'm talking about? You guys remember that? All right, so how about the next ones? Ooh. They don't add up to be 90, right? 15, negative 15 and 75 only add up to be 60. Yikes. But we have a negative angle, so let's change it to a positive angle. So if I have sine of negative 15, is that the same as sine of positive 15? Think on your unit circle. Think about it visually. Are you guys looking at it in your head? Are you like, I like watching you guys take your test because I see some of you guys like kind of like go around a circle and like, and sometimes you have your little finger in the air. All right, so if we're at 15 degrees, is that the same as negative 15 for sine? No, they're opposite, right? So we get negative sine of 15 plus cosine of 75. right? Because it's an odd function. That was from that one box that talked about even and odd. Okay, but we do probably want them to be the same angle. Okay, but now we have positive 15 and 75. Do those add up to be 90? Yeah, they do. So let's change this from sine of 15 into cosine of 75, right? And we still have that negative though. Now, did I have to change that one? No, I could have changed the cosine of 75 into sine of 15, right? It doesn't matter which one you do. What are you guys noticing though? They cancel out, we get 0. Is this making sense? Do you feel better when I use the word proof? Are you like, oh, this is a miniature proof. We got this. This is more of a verify. In the instructions, have you seen verify before? Verify that this is true. All right, so perform the multiplication and use the fundamental identities to simplify. So if you have sine of x plus cosine of x squared, we're going to go ahead and FOIL it out. Don't feel bad if you have to write it out in order to FOIL. I did, even when I was in AP Calc. I remember as a student. Have fun. Oh, here's your homework. Simi. Sorry. So we FOIL it out, so we get sine squared x plus outer and inner. So we have sine of x cosine of x plus another sine of x cosine of x. Let me write them out. And then plus cosine squared. So do you guys see how these ones in the middle are going to combine to be 2 sine of x cosine of x? All right, but then we still have this sine squared and cosine squared. Any ideas? Pythagorean identity, right? Yeah. This and this. What do they make? They make 1. So we have 1 plus 2 sine of x cosine of x. And we're done. All right, 2 sine of x cosine of x actually goes a little bit further, but we'll learn that later in this chapter. All right, so how about 3 minus 3 sine of x times 3 plus 3 sine of x? They're the difference of 2 squares, right? So we know that when we multiply them out, the outer and inner terms are going to cancel. So let's do the 3 times 3 gives us 9. And like I said, the outer and inner become 9 sine of x and negative 9 sine of x. So those go away. So then the last part is going to be minus 9 sine squared x. Catherine's cracking me up. Doesn't it bother you when your hair is all in your face? Okay, so we're going to pull, yeah, Julian's like, I got hair issues too. All right, so we're going to pull the 9 to the front. And when we do you guys see we have 1 minus sine squared? Are you getting to the point where you know what that is? Cosine squared, right? Do you guys see it? 1 equals sine squared plus cosine squared. So if I have 1 minus sine squared, it goes over there. We're left with cosine squared. So I have 9 times cosine squared. And that's it. All right, so I want you guys to try A through D. So try A through D, try to simplify them, see what you get. You can check with the people around you, but don't freak out if you don't have something different. You can be a little bit different. All right, so on number 1, did you guys change everything to sines and cosines? Right now, that's kind of a good process, like changing things to sines and cosines. So cotangent is cosine over sine, and secant is 1 over cosine. So you should get to the point where those cosines cancel. So I saw several of you guys had 1 over sine, which I would count as correct on the test. That's simplified. Or you can simplify it a little bit further, I guess, and call it cosecant of theta, just so you don't have the 1 over. But some people like to have sines and cosines in their final answer. It doesn't matter. All right, so the next one. So we have secant of theta, which is really 1 over cosine, right? So let's get it all in sines and cosines. And then this gets a little bit tricky. So we have sine divided by tangent. So I'm going to do a big bracket so we can think about this. So we have sine divided by, so I'm going to do the old school, that's called an obelus, the old school division sign with the lines and the dots. I know we rarely use those. But if we're dividing by tangent, we're dividing by sine over cosine, right? So what happens when I'm dividing by a fraction? Like sine over cosine is going to become what, Julian? It's going to flip and become cosine over sine. He's already 5 steps ahead of us telling me the final answer here. So we're going to flip it, and it's cosine over sine, and then he was holding up his finger saying 1, right? So cosine, cosine, sine, sine, all of it reduces out to 1. And I'm going to guess that is the most simplified version for that one. So if that was on a test, I would want everybody to get down to 1. There's no question about that one. All right, so let's think about the same way for this. So let's, sometimes it's best to think of it as divided by like that. So if you have tangent squared divided by secant squared, what that is sine squared x over cosine squared x times, well, let's do the divided by still. Divided by secant squared, which is 1 over cosine. Do you guys see what's happening on the next step? We flip it. And our cosines cancel, right? Because we're multiplying across, so things are reducing as fractions. So we're left with sine squared. Again, this is one that I think that would be the most simplified form. I wouldn't take it a step further and write like 1 over cosecant. That seems more complicated to me. All right, so the next one, let's change everything into sines and cosines again. So we have cotangent, which is cosine over sine. Okay, and notice how the argument on this one is u. So use u's, don't change them to x's, keep them the same. Same with thetas. I know you guys don't like drawing thetas right now. Leave them as thetas. So we have sine of u plus tangent was sine of u over cosine of u times the cosine of u. And you can think of these as over 1 if you want to. See what's happening? The sines cancel, the cosines cancel. So we have cosine of u plus sine of u. Now can I call that 1? No, only if they have the squareds, right? So I can't be like, oh, cosine squared plus sine squared equals 1, so that means cosine plus sine equals 1. It doesn't work that way. Okay, that's not equal to 1. So we leave it like that. All right, are we feeling okay with this section? It's not terribly hard. I mean, they definitely get harder, right? I know. I know. I'll ease into it for you guys. I'll ease into it every day, just a little smidge harder. All right, so E. So what do you think if you have 1 over 1 plus cosine of x plus 1 over 1 minus cosine of x? I don't know, like think of numbers. Like what did we do when we had like 1 over, even just 1 over 1 plus x and 1 minus x? If I wanted to combine those into a single fraction, what did I have to do? I had to get common denominators, right? So if you have fractions and you want to combine them into 1 to simplify, then we combine them with common denominators. So think about how we're going to do this. The first one, which is 1 plus cosine of x, needs to be multiplied by what in order to get the same denominator as the next one? So I need to multiply by 1 minus cosine of x on the top and bottom. And the second one, which is 1 minus cosine of x on the bottom, needs to be multiplied by 1 plus cosine of x. So for a moment, it looks a lot harder. It's like, wait, we're not simplifying. We're making this way more complicated. But I promise, it will work.
Pardon the interruption. If you are leaving on the race and E&L field trip, you need to be in the lobby right now. Thank you.
So this first fraction, I'll let you go on your break in a second. This first fraction becomes 1 minus cosine of x, right? Over what? When I do 1 minus cosine plus 1 times 1 plus cosine. So if I multiply those out and I FOIL it out, what would I get? 1 minus cosine squared, right? All right, think about our math rules. Can we reduce these? Yes or no? No. It's just like if I have 1 plus 2 over 1 plus 4, I can't be like, oh, this is going to be 3/5. which is really the same as 1/3. That doesn't work. 3/5 and 1/3 are not the same. Do we understand this? So if we have like things with pluses in between them, don't cancel. You can pull things to the front sometimes and cancel, but we can't do that here. All right, so then we have 1 plus cosine of theta, or cosine of x, over 1 minus cosine squared. So when we combine, the entire numerator becomes what? We have 1 minus cosine plus 1 plus cosine. It becomes the number 2. Do you see it? What about the bottom? 1 minus cosine squared is what? Pythagorean identity. Greta's all over that. The rest of you guys need to be like Greta and like, you see this and you're like, oh, it's sine squared, right? This is sine squared. So we can leave it like that, or you could write it as 2 cosecant squared. Same idea. Okay, go on your break. All right, so F. So it says we have 2 over 1 plus sine of x minus 2 over 1 minus cosine of pi over 2 minus x. So that should kind of, you know, make you think of something. When you see that cosine of pi over 2 minus x, what are you thinking? That's one of those cofunction ones, right? It's going to become sine, right? So this can be replaced with sine of x. Okay, so that means that we have, oh, I'm going to run out of room. We have 2 over 1 plus sine of x minus 2 over 1 minus sine of x. So we go through that same process. We get our common denominators.
I'm confused as to why pi over 2.
Remember those cofunction ones where it was like 90 minus whatever? So like cosine of 50 is the same as sine of 40. That's what it is. So you change it to its cofunction, which is x. All right, so we're going to multiply this one by 1 minus sine of x on the top and bottom, and we're going to multiply this one by 1 plus sine of x on the top and bottom. So when we do, we get 2 times 1 minus sine of x, plus, or minus 2 times 1 plus sine of x. That's going to be our entire numerator. And when we combine them into a single fraction, our entire denominator is 1 minus sine squared. Probably get a new piece of paper. I think I can do that here. All right, so we have 2 times 1 minus sine of x, and then we had minus 2 times 1 plus sine of x. And then on the bottom, we originally had 1 minus sine of x, or 1 plus sine of x times 1 minus sine of x. So I'm saying all of this becomes 1 minus sine squared. Are you with me? Okay. So then the top is 2 minus 2 sine of x minus 2 minus 2 sine of x. Is that what you guys have? And then the bottom is 1 minus sine squared. So what happens is the 2 minus 2 goes away, but those sine of x's don't go away. Yeah? So basically, if you had 2 over 1 plus sine of x, we needed to multiply by 1 minus sine of x on the top and bottom. So the step before this is like you had 2 over 1 plus sine of x. So we're multiplying by 1 minus sine of x over itself. And then the next one was minus 2 over 1 minus sine of x. So we're multiplying by 1 plus sine of x on the top and bottom as well. Do you see that? I'm waiting for the light bulb moment. So that way we get this is here, this is here. Maybe. I think I'm good. Am I good? Did I mess up something else? I don't know. Maybe I did. All right, so I think we get down to negative 4 sine of x all over. Greta? Oh, she's got it. You guys got to be speedier. So we get to there, which you can leave like that. It doesn't go down any further. Sometimes people will be like, oh, sine over cosine is tangent. So you could write this if you brought like sine over cosine and then times 1 over cosine. We'll do this a lot in calculus, but I don't expect you guys to do this here. It'd be like negative 4 tangent of x times secant of x. You don't have to do that. Okay, so you can leave it with the sines and cosines. unless I was asking you to go to that. Sometimes I'll say, get to here. Like, simplify this down and get to here. That's how these identities work. Okay? So let's talk about the graphing calculator ones. So this next one says, you can use graphing calculators if available, or algebraic methods to prove that an equation is an identity. So algebraic methods is what we're doing, getting common denominators, FOIL things out, factoring, right? So graphing calculators, if you are able to use them, and sometimes I'll say you can or can't, you can verify that things are identities as well. So I went ahead and did this on Desmos, but you can do it on the graphing calculator as well, so I'll show you both. So if you're on Desmos, do you see how I put in 3 sine squared x plus 2 cosine of x? Put the sine of x in parentheses. Do you guys all see that here? So I did sine of x parentheses, and then I squared it. Okay? And then I went ahead and typed in the other one, but I didn't want you to see. So that's what that looks like. Kind of crazy, huh? All right. Oh, man, I thought I could. Okay, there we go. So here's the other one. So are those exactly the same curves? No, they didn't match up exactly. So those two are not equivalent. That is not an identity. So this would be no. They don't work out. Right? Now, if you're putting that into your calculator, you kind of have to go through the same thing when you're setting it up. So the left side I would put in for y1, and the right side I'd put in for y2. So you go to your y1. I know you guys can't see this very well. And I would type in 3 sine squared. Okay? If you want, you can try that along with me, but be careful. When you put in 3 sine squared, the calculator doesn't recognize sine squared and then x, right? So you would have to put it in as 3 parentheses sine of x and then square it. Does that make sense? And then you could go through the same thing. You would see that these two things are not equal to each other. So you'd hit graph. It shows that first one. Desmos is just a little bit prettier, right? But what's the sad part? I mean, if I teach you only using Desmos, which is very user-friendly, and you guys enjoy using Desmos, you can't use it on any, like, you can't use it on the pre-calc test, you can't use it on the AP Calc test, you can't use it on the SAT, so you have to learn how to use your graphing calculator, too. I know. You can actually get an app on your phone, which is kind of nice, too. All right, so this one, so it says graph cosine squared x minus sine squared x on a graphing calculator. So if I graph that on here, I would do cosine of x in parentheses squared minus sine of x squared, okay? And I hit enter and I graph. Okay, but like I was saying, this one's it's a little bit harder to read. Like figuring out what the period on this one is kind of tricky. But it looks like the sine curve, kind of, or cosine, right? So can you guys tell what it is? Can you see? It goes up to a height of 1 and down to a height of 1. But its period, it looks like it starts here and ends here. I don't know if that's pi. So let me zoom in a little bit, and I'll show you on Desmos. Like I said, it's a little bit prettier. So let's do cosine squared. You don't even have to do y equals. You can just do cosine. Oops. Bad part about having my last name is Cox. Okay. What I left off the x there, minus. Okay, so here's what it is. So the nice thing about Desmos is if I want to figure out what this point is, I just click on it. Do you see how it's 0, 1? Where does it get to that height again? Right here. So its period isn't 2 pi. Its period is only pi. So if its period is pi, but otherwise it looks kind of like cosine or sine. Which one? It looks like cosine, right? Except only its period's different. So if its period's pi, that means that we have a horizontal compression where y equals cosine of x by 1/2, right? We horizontally compressed it so that it's half the size that it was previously. So what function could this be? Cosine of what? 2x, that's it. And you can check. So if I go back to Desmos and I'm like, is that cosine of 2x? I'm not really sure. Then we put in cosine of 2x, and notice how it is exactly on it. Does that make sense? So what if I did +1, shifts it up, right? Does this make sense? All right, so let's stop there.